Hi, in this video for section 2.8, we will discuss the third objective. The third objective is to determine the validity of a syllogism. That is, to determine if a syllogism is valid or invalid. Now, in the last video, we spoke about kind of comparing a syllogism to an argument. In that, with an argument, we proved that valid or invalid using a truth table. With a syllogism, on the other hand, a truth table is not the appropriate approach anymore, but we need Euler diagrams to prove a syllogism valid or invalid. So we covered this part in the previous video, and now in this video we will pick up right here. So proving a syllogism valid or invalid. First we need to define a counterexample. So a counterexample is a case that shows the conclusion is not true for the given premises. So we will need a counterexample when we talk about proving a syllogism invalid. So let's start first. To prove a syllogism valid or invalid, start by assuming all premises are true. And then we kind of ask ourselves a question. We ask, well, if all the premises are true, does the conclusion have to be true, or could the conclusion be false? Right? So if the conclusion must be true, that means the syllogism is valid. If the conclusion could be false, that means the syllogism is invalid. Okay, so to prove a syllogism valid, you draw all possible Euler diagrams for the premises. Remember, we want all premises to be true, right? So draw all the possible Euler diagrams that could look like. And you have to show that the conclusion is always true in all of those diagrams. This is kind of important, right? That if you find one diagram where a syllogism works, right, where all premises are true and the conclusion is true, that's cool, but you need to investigate all possible Euler diagrams for the premises, right? And if the conclusion is false in just one of them, you still say that the whole syllogism is invalid. Okay, so to prove a syllogism invalid, you draw an Euler diagram for the premises, and you have to show that the conclusion can be false. So note that it only takes one Euler diagram to prove a syllogism invalid. And this one is called the counterexample. Is that Euler diagram that shows the syllogism invalid, right? And then the syllogism is invalid all the time, right? Even if it works for some Euler diagrams, as long as you find that one where the conclusion is false, then the whole syllogism is invalid. Okay, so we have 3 examples here. So example 3, prove the following syllogisms are valid or invalid. So we'll start with 3a right here. So some twins are not identical. Remember we drew that earlier, right? And we said here's kind of the default case that could look like, is that some twins are not identical. So these are your identical twins. So we just need like these twins over here, right? On the left-hand side are those twins that are not identical. So now Mary is a twin, therefore Mary has an identical twin. So we need all premises to be true, right? That's how we prove a syllogism valid or invalid. Both ways, it starts with drawing Euler diagrams where the premises are true. So I have one premise, right, that some twins are not identical. Now I need to make the other premise valid. Mary is a twin. So that's kind of thinking about all the different places you could put Mary. Let me show you what I mean. So like I could put Mary right here, in which case Mary would have an identical twin, right? Because she's here in the identical twin area. But we kind of have to consider all the possible different things this could look like. So you could have twins here, identical twins here. But what if Mary were over here? Remember, we had to consider where both premises are true. So we need Mary to be a twin. But in my premises, they didn't say anything about if Mary's identical or not, an identical twin or not, right? Just Mary needs to be in one of these twin circles. Okay, so Mary could be over here. And this diagram still shows what it looks like for both premises to be true. However, the conclusion, Mary has an identical twin, here the conclusion is false. Right, Mary is not an identical twin. She's over here in the non-identical twin region. So therefore we can say that this syllogism is invalid. Note that the entire syllogism is invalid, right? Even though this diagram looks true, right? The conclusion is true. This diagram shows that the entire syllogism is invalid. So we will say that for part A here, the syllogism is invalid. So now let's try part B. So no winters in Florida have multiple feet of snowfall. Again, to prove this syllogism really valid or invalid, we need to start by drawing an Euler diagram where all premises are true. So remember, our Euler diagram looked like this. Like this was winters in Florida, Florida winters. And then this one is winters that require a snowblower. Or pardon me, this one is winters with multiple feet of snow. Let me say that too, winters with multiple feet of snow. Okay, so we had that Euler diagram before. That is where this first statement is true. No winters in Florida have multiple feet of snowfall. That's what that looks like. So now let's make your second statement true as well. All winters with multiple feet of snowfall require a snowblower. That is also a premise, so that also has to be true in my picture. So all winters with multiple feet of snowfall, let's say they require a snowblower. So that means that winters that require a snowblower, that has to be totally around, right? This winters with multiple feet of snow. That means that every winter with multiple feet of snow is inside this snowblower circle. So here's one possible Euler diagram where both of your premises are true. So now you kind of investigate the truth value of the conclusion. So the conclusion is no winters in Florida require a snowblower. Let me say first that in your notes, I've added this word therefore. That's kind of a key word, right? That points you to this is the conclusion. So that word therefore should be there. Therefore, no winters in Florida require a snowblower. So let's investigate the truth value of that conclusion. So in this Euler diagram, that conclusion is true, right? None of these Florida winters overlap with these snowblower winters. But again, to prove a syllogism valid, you kind of have to run through all the possible Euler diagrams this could look like. So let's try another one. What if we investigate Florida winters? Winters with multiple feet of snow. I'm just going to write multiple, right? But this is the same diagram as before. Florida winters, winters with multiple feet of snow. And what if your snowblower circle, or winters that require a snowblower, what if that looked like this? So remember, we need both premises to be true. Well, the second premise is just all winters with multiple feet of snowfall require a snowblower. So that means we need all of these winters with multiple feet of snowfall. They all better be inside the snowblower circle. But notice I didn't say anything about this Florida winters bubble, right? Does it overlap with the snowblower circle? I didn't say. So this diagram also has both premises true, and in this diagram, the conclusion is false. The conclusion is that no winters in Florida require a snowblower. Well, they could. Like these Florida winters could require a snowblower, right? They're in the snowblower circle. So in this diagram, the conclusion is false. This is called your counterexample. And therefore, we can say that the syllogism in part B is invalid. Okay, let's try part C. Example C. The garbage truck comes on all Mondays. Today is Monday. Therefore, the garbage truck will come today. So your logic might already tell you that that's valid. I mean, seems valid. But let's draw our Euler diagram to be sure. So this one I will do down here. Okay, so C. The garbage truck comes on all Mondays. So let's start by considering all of your Mondays. So this circle here represents, let me put that label inside. This circle here represents all Mondays. And on every Monday, the garbage truck comes. Notice, like, the garbage truck could also come on Tuesdays. I didn't say anything about what happens on Tuesdays, for example. But I said that every single Monday, so this Monday circle, has to be entirely inside the garbage truck circle. Today is Monday is also a premise, right? So that has to be true. The only place I can put Monday, the only place I can put today then is right here. Notice that's the only place. There's nowhere else to put today because today needs to be Monday, so it needs to be inside this Monday circle. Okay, so now we investigate the truth value of the conclusion. So the conclusion is that therefore the garbage truck comes today. And since this Euler diagram is the only Euler diagram representing this situation, the conclusion is true here. Well, that means we can say this syllogism is valid, right? Because the conclusion that the garbage truck comes today is always true. Therefore, I can say that this syllogism is valid. This concludes example 3, and this concludes this video.